So it's a bunch of guys in lab coats standing around a table with what looks like a melted plastic inflatable human on it. But the caption says, "My God, it is Professor Dickel. Weinberg, see if you can make out what the devil he was working on, and the rest of you get back to your stations." Which is kind of how people think scientists work. Is that we're not really, we're just interested in results, and somebody melts on their table. It's like, okay, nothing to see here, go back to work. So, science is testing. If somebody comes up with a great idea, a hypothesis, oh, I think this is what's going on. I think this is why this is happening. Then if they're in a room full of science people, the response they're inevitably going to get is, oh, that's really cool. That's really interesting. How do you test that? Because if you can't test something, then it just is, it's an idea. Is it, you don't have any support for it, except other people go, oh, that's really cool. And in some areas of science, more than others, that can be enough. Is that it seems like from what I read from physics, because I do read up on all the sciences, sometimes with physics, if you can get the math to look pretty enough, even though there's no real practical, real world way of testing something, if the math looks pretty enough, people kind of accept it. How do you test something? You got to be able to make predictions based on your idea. You got to go, well, if I'm right and we do this, then this should happen. So the tests lead to results. Now the classic original, remember I say people get responsibility, lots of people are working, but there'll be one good story that winds up being kind of the historical connection for this. Here's our one good story. People used to not understand where a lot of stuff in the world came from because they couldn't see it. Is that they knew that after the winter went by that there were living things in the stream, but they didn't know where they came from. Is that the stream seemed to have been, it was too cold over the wintertime. They weren't, how were there fish there? They couldn't find the eggs. Where'd the snails go? And they used to think that when the world got warmer, that certain of the rocks would change into snails, and certain of the leaves that had dropped into the water would form into fish, because fish are flat and roughly leaf-shaped. The idea that you can get living things from stuff that's not alive is the idea of spontaneous generation. And one example of spontaneous generation that people believed, and if you think about it, it makes sense, was that meat left out long enough, the surface would turn into maggots. Now, Reddy was pretty sure that wasn't what was going on. The meat did not turn into maggots. In fact, he was pretty sure that the maggots were somehow associated with flies landing on the meat. But think about this. We know flies land on the meat, they lay eggs. Now, the eggs are too small for these people to have been able to see. The eggs hatch into teeny little maggots, and the maggots start to eat the meat. And as the maggots grow, the area that they're in is a hollowed out piece of meat. It looks like a piece of meat changed into the maggot. But Reddy went, no, I don't think that's what's going on. And I'm gonna run a test to show you that the meat doesn't just kind of magically turn into maggots. So he set up meat in 2 containers, a test container and a comparison container. Classic scientific method is that let's see if what we think is happening, and let's run a test where we're not going to do that and see if we get the same results in both tests, then what we think is happening isn't happening. I'll come back and cover that. It'll make more sense. So a container, an open container that the flies could get into, and a closed container that the flies couldn't get at. And he set it out for a couple of weeks. And sure enough, after a couple of weeks, the open container was full of maggots and the closed container wasn't. Now, this is also kind of an example of how science works. And he went, look, look, look. And he went, well, and the people went, well, no, you can't expect the meat to change into maggots in a closed container. Is that you need air circulation for the meat to turn into maggots. Because they do know that if you lock somebody in a closed thing, is that bad stuff would happen. They figured the meat was in the same situation. So he went, okay, I have to redesign my experiment in the light of your criticism. And so he, instead of putting a hard cover on the second test container, he put cheesecloth over it. Because you could blow through cheesecloth. Pretty obviously air could go through it, but flies can't go through it. And sure enough, he got maggots in the open container and no maggots in the cheesecloth covered container. He was kind of lucky that flies couldn't drop their eggs through the cheesecloth. And that's kind of given as a kind of a Renaissance example of very early scientific method. A test, a comparison test, see how the results are different, and the results should hopefully support your hypothesis. If they don't, you've run into what's called the null hypothesis, which is basically the idea that, you know that idea you had? It's wrong. Is your results don't support it. In fact, they support the exact opposite, the null hypothesis. But observations lead to hypotheses. You know, you might be right about the house tilting. So, controlled experiments. Now, sometimes what happens is you wind up with a term associated with something, and it winds up sometimes being more confusing than it's useful. The idea of control is people think, what happens when you control it? Well, you somehow make sure you know everything's happening that you think is happening. A control test isn't really controlling the way that we use the word in English. It's just a term given to your comparison. Your experimental test you set up to test your hypothesis. And then your control test, you change what you're testing now in a really classic experiment, you take away the thing you're testing. You run the same test with the thing you're testing, without this thing you're testing. Can't always do that. But think about the vaccine tests. What do? Well, we give people an injection with our vaccine, and we give the control people an injection with just salt water in it, just salt that matches the salt water content of your body. And so they're getting, as far as they know, they're getting exactly the same treatment. And then you look to see, you track them for a while, and for the vaccine, see who, in the case of the coronavirus vaccine, see who shows symptoms and tests positive for coronavirus. And that's actually part of science that gets tricky. Because how do you decide your thing that you think is happening is actually happening? The coronavirus vaccines have been criticized because they're not testing to see if people are getting infected. They're not running the coronavirus tests on everybody. They are letting people out into the world, and when people get symptoms, they come in to get tested, and then they see if they actually have coronavirus. And since coronavirus can be in people and they don't have any symptoms, and in some cases they can be contagious without any symptoms, the idea that they're only testing for symptomatic disease, some people have really criticized. But you've got results, you've got no results. When they say 95% effective, what happened was they tracked it for a while. They got a few cases of confirmed coronavirus in the test group, the group that had actually gotten the vaccine. They got a bunch of cases of coronavirus in the people that had gotten the fake vaccine, the placebo. And the difference between the two is a 95% difference, is that the odds of catching it without the vaccine are 95% better than the odds of catching it with the vaccine. So again, you compare your results. And since they were originally looking for a 50% threshold, 95% turned out to be pretty good. And some of the vaccines are coming back with 93%, and I think the Johnson & Johnson is 73%. But one of the vaccines is actually testing for coronavirus itself, not testing for symptoms, but testing for infection. And so their results may not look the same because they're actually measuring something different at the end of what looks like the same experiment. Any experiment that you run is going to wind up with confounding factors. Confounding factor for Reddy's experiment was people wouldn't buy his results because he had sealed the container. And they went, no, that's messing with what you think you're testing, as that's a confounding factor. And he didn't think it was, but he could set up an experiment to take that into account. And you can fiddle with your experiment to try to remove confounding factors. One famous confounding factor that you get in medical tests, this is just an example, is the placebo effect. You treat people and they feel like they've been treated and they may feel better. Now, the placebo effect is not going to make your cancer go away, but it might make your headache go away. It may not make your cancer go away, but it may make you feel less sick. So it may improve your quality of life. In the case of the vaccine tests, this gets a little tricky because the vaccines very often produce symptoms, right? Your arm hurts for a while. As my wife got the vaccine, her arm hurt for a few days. She actually got a little loopy in the head, felt fatigued, very common side effect of the vaccine. And a lot of people who got the placebo, who understand how this works, like 2 days later, they haven't had any effects except, that one needle feel in the original. They go, well, I don't think I got the real vaccine. I got the placebo. So are they going to feel treated in that situation? Are they going to feel cheated in that situation? That's a confounding factor. And in fact, some people have suggested that a proper control in the vaccine trials is to give them a vaccine for something else that also has similar side effects, makes your arm sore or something. Another vaccine's been out on the market for a while. It's not going to, have any bad side effects, but it's going to have side effects because they'll say, well, if the treatment group gets side effects and the placebo group doesn't get any side effects, that's already a confounding factor. They're not really a comparison anymore. And why does that matter? Well, what are people doing? They're going out into the world after they've been test vaccinated. Well, the people that are sore and have side effects for a couple of days, they feel a lot more immune, and so they may be engaging in more risky behaviors. The people that pretty much decide, oh, I don't think I got the vaccine, if they were careful before, they're going to continue to be careful because they don't feel like they're protected. What's that going to do to your two groups? Who knows? This is why you want the groups to be as comparable as possible. And the placebo effect is a particular type of confounding factor. An artifact is a result from an experiment that just comes from the way you ran the experiment. The difference in coronavirus in your two groups may be an artifact of the artifact of that the people could tell they weren't vaccinated. The way you ran the test, your placebo group, a lot of them figured out they were placebos. They might not have gotten exposed as much as your test group. Your results are different, not because of the vaccine protection, but because of the behavior difference. That's an artifact, is that there's a whole bunch of ways that you run an experiment. The whole idea of giving shots to both of them is, when they originally used to do this, they'd give a shot to the people that were sick, and then they would compare them to people that were sick that they hadn't really treated. Because they didn't, it took a while for people to figure out there was a placebo effect that might have an effect on the test cases. Originally, even when they did mouse studies, you'd have a whole bunch of sick mice, you'd have your experimental mice over here, you'd have your control mice over here, you'd take your experimental mice out and do whatever you were gonna do to them and put them back and compare them to the sick mice that you weren't doing anything to. And somebody finally went, well, what we're doing to these mice is probably stressing them. It's probably having an effect on this illness beyond our treatment. We should be doing that to these guys too. So if we're giving these guys shots, we should be giving these guys shots. If we're giving these guys special food, we should be giving these guys, something like the special food, but without the variable in it, is to treat the groups the same as much as you can. And in this case, the variable is just giving them special food, but you're varying is what's in it in both of them. They ran a test on PCBs. I was in a conference for, and they gave rats salmon. PCBs accumulate in the fatty tissues of salmon, so they gave them salmon. But they gave the experimental group salmon from around here. That picks up PCBs from the pollution here. And they gave the control group salmon from the Pacific Northwest, where there's no PCBs in the meat. So that's a pretty good experiment. You're treating them both the same. They're getting the same food. It's just there's PCBs in one group and there's not PCBs in the other group. And then you test them for, if I had more time, they got some pretty doggone weird results. Well, I'm going to pause here. I feel like I want to tell you that story. I'll tell it to you on the next video.